Welcome to day 3 of chapter 7. We are still in section 7.1 radian measure, but today we're going to talk about angular speed and linear speed. Now today there's going to be a lot of variables being thrown at you, but the big thing is to understand the formulas, and then really any variable you want to use will suffice. So I'll explain what I mean. So suppose that a wheel rotates about its axis at a constant rate. Looking at this picture, the radical line turns through an angle at time t. So picture A is talking about this angular speed. I'll kind of highlight this formula right here for us. So angular speed is used with the Greek letter W called omega. Use it if you want, don't if you don't. And it is theta divided by t, and t is time. One thing to make sure we remember is any angle measure, when we're putting it in a formula, needs to be in radian, just like day 2. So you might have to do a little bit of conversion. But this is angular speed, the actual speed that the angle is changing. Versus, if we look at picture B, we're now talking about the linear speed, where this physical point is moving. So if you look at figure 13b, if point P is on the rotating wheel, travels a distance d, so this d, that distance that point physically travels during time t, in that interval, then the linear speed is denoted with the letter v equals d over t. Now keep in mind d is something that we looked at yesterday. D is really that arc length. So if you want to instead call that S, because yesterday we called it S with arc length, go for it. A lot of formulas, yes, but we're going to look through on how to plug in, but they're very, very different. Angular speed is how the angle rotates. Linear speed is how a physical point travels. Let's try a couple. So calculating angular and linear speed. A circular gear, kind of like in the picture, rotates at a rate of 100 revolutions per minute, or RPM. What is the angular speed of the gear in radians per minute? So we're going to have to look at units. So angular speed is given by this formula up here, but before we can plug in, we have to do a little bit of algebra because the numerator needs to be in radian. All I'm given here is that I have 100 RPM. That's not radian. So I'm going to start with my angular speed. This is what I'm shooting for, that my omega equals my angle over the time, but I need to have the numerator in radian. Right now I'm given 100 RPM. That's revolutions per minute. Revolutions per minute means how many times you physically go around the full circle. So from here all the way around is a revolution. 1 revolution. So they're doing 100 revolutions per minute. That's going really, really, really fast. Well, we know each revolution, a full circle, is 360 degrees. And from our day 1 and 2, we know 360 degrees is really 2 pi. So I'm going to do a little over here. To get my angle, I know each revolution is 2 pi. So I'm going 100 revolutions is 2 pi radian. So 100 times my revolution. So really my angle here is 200 pi radian. That is my numerator. Because you need the numerator to be in radian, we were given it in revolutions. So that's not the correct unit, so you had to do a little bit of conversion. Then we look at time. It says find the angular speed per minute, so time is just 1 minute. And then we kind of simplify those units. So really, you're going to have 200 pi radian per minute. That right there is your angular speed. You have it in terms of radian in the numerator, and your unit is minute in the denominator. Okay, that was part A. Part B now wants us to find linear speed. So that's our equation down here, V equals d over t. Remember, d is the arc length. So we're finding the linear speed of a point on a gear 4 centimeters from the center. So here's my formula that I'm going to plug into. But my numerator has to be the arc length. So think back to yesterday, arc length, d or s, whichever value you want, equals our radius times your angle in the middle. Well, we just found that angle in the middle from part A, right here. That is the angle that helps us find the arc length. So this would be my 200 pi. So really my arc length from my formula yesterday, arc length is really 800 pi in our units. This is centimeters. So that becomes my arc length on top, my numerator. And my denominator is still going to be 1 minute based on the first problem. So they kind of build together. Then we're going to simplify by just kind of combining our units. So we're going to have 800 pi centimeters per minute. There we go. Squeeze that in. That is your linear speed. So just to start, we do everything the same. We start with our equations. But here we have to do a little bit of algebra before we can plug in based on units. So for the first one, I had to find my angle in radian. And the second one, I need to make sure I found my arc length before I plugged in. One last formula for you. Suppose an object travels at a constant rate along a circular path. Then the linear speed v and the angular speed omega are related by this equation. So this is our third and final equation that actually relates the two that we learned before. Angular speed must be expressed in radians, just like before, just like we've written down up here. Needs to be in radian. But now you can relate them together. Pretty cool equation. Let's see how we can use it on the back. So a CD rotates 180 revolutions per minute. Calculate angular speed and linear speed for a point 6 centimeters from the center. So here it looks like we're just going to use both of our formulas from above. We're not relating them, so we're not going to need this one as of right now. We're kind of doing two separate problems, kind of like an A and a B, like we did above. So the first one, let's calculate angular speed. So when we do angular speed, I like to just write down the equation. The omega equals angle over t. The angle here, we're not given an angle. So we're going to have to do a little back knowledge here. The angle, I'm given 180 RPMs. So I'm going to take my 180 revolutions, so that means one time around the circle, times what is the measure of the circle? Well, it's 360 or 2 pi, because we need to be in radian. So my angle is 360 pi radian. That can go right in my numerator now. Because I have the correct units, I can plug in. Now, here it's not giving us an actual unit, but because it says per minute, that's also a giveaway that the denominator is just going to be one minute. So overall, your angular speed is going to be 360 pi radians per minute. That is the speed of your angle. Last one is linear speed. Writing down this formula from above, V equals D over T. We again have to do a little bit of math because D is the arc length. All we're given here is that it's 6 centimeters from the center. So to find my D, which is the arc length, this is a formula from yesterday, arc length is the radius times that angle. Well, we found that angle again in part A, or angular speed. It's right here. So just like we did in the last problem, we're going to plug that in right here in order to find my arc length, which is going to be 2,160 pi centimeters. That is my distance, or my arc length. And again, our units on the bottom is going to be that 1 minute because it's revolutions per minute. So my linear speed overall is 2,160 pi centimeters per minute. That is how fast the actual point travels, centimeters per minute. Versus the angle you can see is radian per minute because it's an angle. An angle is represented in radian per minute. Arc length is a length, so centimeters per minute. One last thing, we're now going to use our new formula at the very end. V equals R times omega. And let's just try this belt problem. So a belt connects two spinning discs. Okay, you've probably seen something like this somewhere in your life. If the radius of the larger is 15, so I'm just going to put that in here, 15 centimeters. The radius of the smaller is 5 centimeters. And the angular velocity of the large is 3,000 RPM. Look at that. It's already giving it to us. Find the velocities, both linear and angular, for both disks. Okay. Oh, I'm so sorry. Bless me. Wake you up a little bit, right? So let's start with the larger. So we're doing everything for the larger disk. Let's start with the angular. Angular speed. Okay, so we know the velocity of the larger is 3,000 RPM. That's why I'm starting with the larger, because otherwise I have nowhere to go. Like, I don't know the RPMs for the small. So this is kind of telling me, okay, this is where I'm going to start. Angular, keep in mind, is this formula. But we can't have RPMs in the numerator. We need radian. So a little bit of math here. We're going to find that angle using our 3,000 revolutions per minute. And each revolution is one circle. 2 pi. So our angle now is 6,000 pi radian. So we got our units we wanted. I'll just put that in there because the numerator has to be in radian. And then, this problem also does not say minutes. So since it's revolution per minute, again, we're going to use the idea that it's per minute, so 1 minute. So overall, I'm going to move this out of the way a little bit. Our angular speed is going to be 6,000 pi radian per minute. That's the angle. It's going to rotate in radians because that's a measure of an angle per minute. Now we'll find the linear speed, still of the big. And again, we're starting with the big because we know that revolution per minute. Well, this formula is D over T. The distance needs to be in terms of the arc length. So let's do a little math for distance. Is the radius times the angle. Again, we found that angle in the beginning. 6,000 pi. So my arc length is actually 90,000 pi centimeters. That's my distance. If you're having trouble with arc length, please go back to yesterday's notes. It's going to be per minute again. So really, this is how fast a single point will travel. 97 pi centimeters per minute. Since it's distance, we have a unit of distance, centimeters. This is all for the large. So we just found the angular speed and the linear speed for the large. Now we have to find for the small. So kind of running out of room, but that's okay. So for the smaller one, keep in mind we are not given the RPMs. We don't know what the revolutions are. So angular, we'll have a quick second. We'll figure that out. Linear, though, do you see how this is the same line? Sorry, is it going this way? Hello. This kind of line or rope around the disc are going to keep moving. It's the same line. So actually, the linears will be the same. So linear speed, it's not that, oh, when it gets closer to the big, it's going to go faster. No, it's going to have the same constant rate. So the linear speed is going to be the same, 90,000 pi centimeters per minute. Okay, it's going to be the same because it's the same string. However, when we find angular speed, this is when we're going to bring in that last formula. So our angular speed, we're kind of at a loss. We don't know where to go because we're not given the revolutions per minute. But we're given this formula at the very end to help us relate them. So let's use that. Okay, it's going to help us find our omega, the W that we're missing. Let me show you what I mean here. So we're going to use this formula to help us. We know the linear speed from above is going to be that 90,000 pi. We know our radius of the smaller is 5. And we're solving for our angular speed or our omega. So just divide both sides by 5. You'll get that your angular speed is 18,000 pi radian per minute. And this should make sense because it's angular, so we're talking about radian per minute. This is just our first day on this. If you have questions, let me know during class. But the big thing is to use your formulas, but make sure you have the proper units. Good luck, and I'll see you in class.